In this video, we will discuss Taylor's theorem, which is an important generalization of the mean value theorem, and it's important because it's useful in approximating functions with polynomials. So it's really quite amazing because no matter how complicated the function, as long as it satisfies some criteria here, you can approximate it with polynomials, which is easy to evaluate and compute. So Taylor's theorem here, we will discuss Taylor's theorem, and we'll do a bunch of examples. The first thing we should do is look at Taylor's theorem itself. So let a function f and its first n derivatives be continuous on the closed interval ab and differentiable on the open interval ab, and let x naught be in the interval ab. Then for each x in ab with x not equal to x naught, there exists a point c between x and x naught such that f of x is equal to f evaluated at x naught plus f prime evaluated at x naught times x minus x naught plus f double prime evaluated at x naught divided by 2 factorial times x minus x naught squared plus on down to the nth derivative evaluated at x naught divided by n factorial times x minus x naught to the nth power plus f to the n plus 1 power evaluated at c divided by n plus 1 factorial times x minus x naught n plus to the n plus 1. The formula is quite long, but it's not that hard to memorize because if you notice, when you're at the nth derivative, you divide by n factorial, and the exponent on the x minus x naught is n. So for example, when you're on the second derivative, you divide by 2 factorial, and the exponent on x minus x naught is equal to 2. There are two things we will note, but we will look at in more detail later. Since x is not equal to x naught, so these terms are not equal to 0, it's always possible to solve algebraically for this last term, which we will call m. The second thing to note is that Taylor's theorem is an extension of the mean value theorem, and we will look at that more in a moment. We talk about the Taylor polynomial for f at x naught, and this polynomial is essentially an estimate of the function f evaluated at x naught. And we can have a very simple, quick and dirty estimate that is polynomial of degree 0, so we call that p0, p for polynomial, degree 0 of x, and we set that equal to f at x naught. So that's our first estimate. A little more complicated and closer or more accurate estimate would be the polynomial with degree 1, and that's p1 of x. That'll be our f of x naught plus our next term, f prime of x naught, x times x minus x naught. And then p2 will give us all of the polynomial of degree 2, so that will be our first 3 terms. And our nth polynomial will be our polynomial of degree n. And then we have our remainder or error estimate, which depends on the term with the f to the n plus 1 derivative. And now is a good time for an example to look and see how all of this fits in. So we're going to find the nth Taylor polynomial for the function f of x equals e to the x at x naught equals 0. We're going to compute for n equals 5. In other words, we're going to compute p5, which gives an estimate up to the 5th derivative. Looking to see what we need, we do need to evaluate f at x naught as well as f prime at x naught, f double prime at x naught up to fn, up to n equals 5, f5 of x naught. And what we can see is the nth derivative of e to the x is just equal to e to the x. So f of 0 is equal to e to the 0 equals 1, and that is equal to all of our derivatives. I have written my formula for Pn of x, and I have plugged in for x naught, which is equal to 0. So I have my 0 here, my 0 here. And now I can plug in f of 0 is equal to 1 plus my f prime at x0 is just equal to 1 here times x minus 0, which is x, plus f double prime of 0 is equal to 1 divided by 2, so that's my 1/2, times x minus 0 squared, which is just x squared over 2. So my nth term is going to be 1 over n prime and then times x minus 0 to the n. So this is my nth term. I have my formula for my remainder, which is f to the n plus 1, evaluated at c over n plus 1 factorial times x minus x naught. X naught is just equal to 0, so it's x to the n plus 1, which is equal to the nth derivative, nth plus 1 derivative of f is just e to the c, or e to the x. In this case, plugging in c, we'll have e to the c times x to the n plus 1 divided by n plus 1. So finally, for the fifth Taylor polynomial, that's p5 of x, I have 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial plus x to the fifth 5 factorial. And now all that remains is to compute the remainder. For R5, I'm going to plug into my formula EC x, in this case n is equal to 5, x to the 6th divided by 6 factorial. So the remainder really depends on where we are in the real numbers. So if x, let's just say x is in the interval between -1 and 1, so our c, which is going to be close to x, is also between -1 and 1. So R5, its top number here, when c or x is equal to 1. So R5 is less than e raised to the c, which is e raised to the 1, divided by 6 factorial, and then my 1 to the 6, which is just 1. So my remainder is bound, and it's going to be less than 0.0038. So you can see the fifth polynomial is actually quite a good estimate for e to the x. Using a different f of x, which I have graphed with this black curve here, I don't have a formula for it, we can look and see what these Taylor polynomials are. So we have this function f of x, and we're looking at it on an interval ab. So here I have my a and b. And then our x naught is something in the interval ab, and I put it at the midway point. It doesn't have to be. So then what we're saying is if we want a first approximation to what f is on this interval in AB, we can take f of x naught, this is our approximation of polynomial of degree 0. Our first approximation would be f at x naught, so that's our p of 0. And so all along, we're just going to use this line, y equals p naught of x is equal to f of x0. So this is our estimation for what f of x between a and b look like. And remember, generally a and b is a kind of a small interval. Hopefully x naught is somewhere close, there's not a huge distance. So this isn't a bad estimate, this here for a and b. But of course, as you go further away, further out, then it gets not quite as good. But what you can do to improve that is to take p1 of x, which is now a line, and it's the tangent line over here, plus f of x naught. So here, we're going to have a little bit of a better estimate of what f of ab looks like using the derivative, more information. As we go, as we increase, to f double prime, we're going to have more and more information, and we'll be getting closer and closer to the correct values of f in between a and b. And now we're going to look at the proof of Taylor's theorem. We're going to fix x in our interval, and x is not equal to x naught, and we're going to let m be the unique solution of, and here we write Taylor's formula, f of x is equal to f of x naught, f of x1 up to f of xn, plus whatever error there is, or whatever the difference is between this Taylor's formula and f of x. And our proof is going to consist of showing that this error here is equal to this term here in our Taylor series. And recall c here is some number between x and x naught. We are going to define our new function, capital F of t, and it looks a whole lot like f of x. So it's going to be f of t plus f prime of t times x minus t to the first power plus all the way up to f, the nth derivative of f of t over n factorial times x minus t to the nth power plus our error term, well, not quite the error term because it's m times x minus t to the n plus 1. And we see f, because it is a polynomial, it's continuous on the interval ab and differentiable on the open interval. Now when I plug in x for t and my capital F of t, my capital F of x is going to equal to f of x, f prime of x, x minus x, so that goes to 0, and all these other terms go to 0, including this one here. So what I get is capital F of x is equal to lowercase f of x, and then my f of x, I plug in my Taylor series expansion over here, or my Taylor series. I can plug in x naught into my capital F, so I have capital F of x naught is equal to little f of x naught times derivative of f of x at x naught, etc. So then if you look, what I have is f of x naught is equal to f of x. Where's f of x? Over here. So big F of x naught is equal to little f of x. By the mean value theorem then, I have a c in x to x naught. Again, this is the mysterious c over here, also mentioned over here, such that f prime of c is equal to the derivative of f of x minus f of x naught over x minus x naught. And now over here, our f of x is equal to little f of x, which is equal to f of x naught. So this numerator over here is equal to 0. So our f prime of c is equal to 0. And we also want to note when we compute the derivative of f of x, we find all the terms except the last two cancel in pairs. So for example, f prime of t, x minus t, must be differentiated using the product rule to get f double prime of t, x minus t times minus f prime of t times derivative of this with respect to t, which is just -1, which is why you get the negative. Thus, this derivative here, which is equal to 0, is equal to everything canceling except the last two pairs. So that will be our f of n plus 1 evaluated at c over n factorial, x minus c to the n, minus m n plus 1, x minus c to the n. Since these two, this subtraction is equal to 0, that must mean these two numbers are equal, and so we have m is equal to this over here, the f of n plus 1 evaluated at c n plus 1. And thus we have completed our proof. And to see the relation between the mean value theorem and Taylor's theorem, I have the mean value theorem written here. So if f is continuous on the closed interval between a and b and differentiable on the open interval, then there exists at least one point c in ab such that f prime of c is equal to f of b minus f of a over b minus a. So I have this derivative here for f prime of c according to the mean value theorem. And then I just rearrange the terms. So I have f of b is equal to f of a plus f of c, f prime at c, b minus a, and this will be our error term. So this is essentially then this Taylor formula for n equals 0. So that's just without the derivatives here, but with this last term for our error term, our x is equal to b, so we're trying to estimate f at the point b, and our x naught is equal to a. So our first estimate of f of x at point b is using f of a. So this is our estimate. We're estimating f of b using f of a. Here is our error term, which is at the very end, which is f of n plus 1. And again, since we're at 0, this is f prime at c at over 1 factorial times b minus a to the first power. So these two, that's basically the relationship. For our next example, I have the problem of finding the third degree polynomial for f of x equals 1 plus x to the 1/2 for x greater than -1 using x naught equals 0. I started by writing the formula since they want the third degree polynomial for p3 of x. And I just kind of extended this, plugging in n equals 3. And then I plugged in for x naught equals 0 into this formula to get this far. Next, I need all the derivatives and things, and then I need to know what it evaluates at x naught. So I have f of 0, f of x naught is equal to 1 when I plug this in here. I have f prime of x here, and then f prime at 0. and then I went up to the fourth polynomial. And even though I only wanted P3, I needed the fourth derivative to get my error term. Finally, I plug all this into my formula here to get P3 of x is equal to 1 plus 1/2 x plus minus 1/4 times 1/2 times x squared plus 3/8 times 1/6 times x to the third. And here you see my remainder term, minus 5/16 times 1 plus c to the minus 7/2 times 4 over 4 factorial. For my next example, we have the fifth Taylor polynomial for f of x equals x to the third plus 4x squared minus 3x plus 5 evaluated at x naught equals 1. You can see my calculations, and then P5 is equal to 7 plus 8 times x minus 1 plus 7 times x minus 1 squared plus x minus 1 cubed. You can see the fourth, fifth, and sixth derivative are equal to 0. So P5 and P4 is equal to P3. So actually P5 stops at the third power, which kind of makes sense because our f of x is only the third power. Also, f of x, since the sixth derivative is equal to 0, we also know that our error is equal to 0. So in this video, we covered Taylor's theorem with the formula here and our example over here. I have one problem for you to try, so pause the video, give it a try, and on the next slide, I will have a solution for you. Here is the solution. And that is it for this video. Thank you for watching.